Permutations with restrictions is one of the most common ways students lose full marks in exams. Not because the maths is hard, but because they count arrangements that aren't actually allowed. For example, a question might say two people are not allowed to sit next to each other, okay? And say you have a total of people, and most students will just still use the factorial 6 factorial straight away and get an answer like 6 factorial, which would be 720 different arrangements. However, the problem is that answer is completely wrong and the marker gives 0. So you will get no marks for that if you don't know how to use restrictions with your permutation calculations. So in this video, I'm going to show you a step-by-step method that works for every restriction question, including not together, must be together, and fixed positions, such as being in a specific place and it can't be moved from that pre-selected position. So hopefully by the end of this video, you'll know exactly what to do the moment you see one in an exam. So let's do a warm-up. How many different arrangements can be made using all of the letters of the word cat? So remember from our previous lesson, we have the box method that we can use. If there's 3 letters that we have to use all the letters, right? And there's 3 different letters. Then for the first letter, we have 3 options, C or A or T, times by the 2 and then the 1 different possible outcomes. So we get an answer of 6 different arrangements. Okay. Same thing with math. All right, we just be doing basically 4 factorial, which is 24 different arrangements. However, if we look at section B, where objects must be together, our block method, then so question 3 asks us how many different arrangements can be made using all the letters of the word team. So that's going to be 4 letters. If the letters T and E must be next to each other. Okay, so the block method basically says that, okay, let's say that T, E being together is one set, okay, or one set as its own, and then we have A and M as our other sets, okay? So basically what we're saying now is we have a total of 3, I guess, sets slash like letters, or in other words, like the box method, we have boxes, okay? So what that means is that if you think of it logically, right? Let's say that we have T and then E. So let's look at that possible combination first. We can either have it in the beginning, like team, or we could have it like A, T, E, M, or we can have it in the end where we have our T, E in the end. So A, M, T, E, okay? And that would be that there. So, however, obviously within those letters, we can also rearrange and make it ET, right? We can swap around the T and E, and same thing with the A and M as well, I guess. So that would mean that we have much more possibilities, okay? And so what we can do then is the block method says that we have 3 boxes, right? So we have 3 different sets that we can put. So we do 3 factorial, okay? So that gives us 6. But given that one of our blocks is multiple letters, we can have multiple combinations for that box, okay? So TE can be rearranged and become E and then T, okay? Because again, it's asking how many different arrangements, so it really cares about the order of things. So order does matter in this question. So in order to account for that, we basically just do times by 2 factorial, because obviously if we have 2 letters, we can arrange it in 2 different ways, and that makes sense because we have T and then E, and E and then T as our 2 different arrangements for T and E having to be next to each other. Okay, so we can either get TE or ET. So we consider that by doing our 2 factorial and multiplying with our calculations. So essentially 3 factorial times 2 factorial, which is equal to 12 different arrangements. Okay, and again, using stuff like the multiplication or AND principle, we know that we have to be multiplying these numbers because they are happening simultaneously. Okay, they're happening at the same time, and yeah, that's why we use the multiplication rule for probability. So let's see the next one. How many different arrangements can be made using all the letters of the word school? So school has 6 letters, but if we have S and C being together as one block, then we technically only have 1, 2, 3, 4, 5 different boxes. Okay, so we need to have a 5 factorial in there. All right, so that's going to give us 120. However, within S and C, we have 2 different arrangements. 2 factorial different arrangements. We have SC or CS. So we have to multiply our 120 by 2 to get an overall answer of 240 different arrangements. Okay. Cool. Next one, in how many ways can 5 students line up if Alex and Ben must stand next to each other? Okay, so again, similarly, let's say we have Alex being A, Ben being B, and let's just say the other 3 students are C, D, and E. A, B, C, D, E. Okay, if we have A, B as a block, and then we are going to have 1, 2, 3, 4 different blocks, we have 4 factorial. Okay, multiply that by the number of different combinations we can have for Alex and Ben. So we have AB, or we have Alex and then Ben, or we have Ben and then Alex, BA, which is 2 combinations. So we have 4 times 3 times 2 times 1 times 2, which is 48 different combinations. Arrangements for that. Okay. Section C, this is the opposite now. So where objects cannot be together. This is the exclusion method. So how many different arrangements can be made using all of the letters of the word team if the letters T and E cannot be next to each other? Okay. So the trick here is to do the total, right? So the total number of different arrangements that we have, right? So 4 factorial. If we were just doing this part of the question, not this part. So for example, we ignore the second part of the question. So we have the total number of different arrangements, right? So 4 factorial is 24. Okay. But now we start looking at the next part, and then we do the complement or the opposite of what it's saying, right? So a good trick in probability is that if you have a cannot in your question, you can do total minus can, or the opposite of cannot, which we indicate as a dash. So cannot dash is actually the opposite of cannot. So basically what I'm saying is, in simple layman terms, we have the total number of arrangements if we were just to do team minus the T and E have to be next to each other? Okay, so the number of arrangements for that. Because from our previous section, we know that there are 12 different arrangements where T and E have to be next to each other. So by logic and probability rules, if we know the total number of different arrangements for team, and we take away the total number of arrangements where T and E have to be next to each other, then we are left with T and E not next to each other. Okay, we basically get a formula where we get the number of different arrangements where T and E are not next to each other, because we did the total arrangements minus the arrangements where T and E have to be next to each other, which is the opposite. Okay, so that's a good trick there to use. So if we know the total is 4 factorial, we just minus our 12 that we got in the previous question, right? And that 12 came from the 3 factorial times the 2 factorial, as we mentioned. Okay, and so we get a value of 12 as well. Question 7, 6 people are standing in a line. In how many ways can they line up if 2 particular people must not stand next to each other? So again, using the exclusion method, that's what I'm going to call the opposite method from now on. Let's just do 6 people in general if there was no restrictions. So the total will be 6 factorial, okay, which is 6 times 5 times 4 times 3 times 2 times 1, 30, 120, 360, 720. And then if 2 particular people must stand next to each other, so the opposite of what it's asking. So 2 must stand next to each other. Then we're going to have 5 blocks factorial that times the 2 different combinations we have. So that's going to be 120 times 2, which is 240. Okay, and from that, I can just do my formula where for this outcome where 2 particular people must not stand next to each other, we do the total minus the complement, okay, or the opposite of what it's asking, and then we get the outcome, which is the 2 particular people must not stand next to each other. So we have 720 minus the 240, and that gives us a value of 480 different arrangements. Question 8, explain why the method total permutations versus unwanted permutations is required for this type of problem. Yeah, so again, that's sort of the formula in, I guess, neater terms, if you want to see it like that, that I've been using for question 6 and question 7, right? We do the total permutations if there were no restrictions minus the opposite of what we want in terms of our outcomes, okay? And then we'll get our value is going to equal the permutations that we want, right? Which are the restrictions, such as the objects cannot be together, okay? So in terms of explaining why this is required for this type of problem, just I would say that this method works because it's often easier to count all possible outcomes, okay, because that's easy. We can just do a factorial of a basic number for that, typically, and then subtract the ones you don't want. Okay, especially if they're mutually exclusive. That's where you can only use it. So it's either you are next to each other or you're not next to each other. There's no other third variable or like intersection for that. It's complete opposites, and so you can use that formula for this type of problem as well. So I might also mention mutually exclusive permutations. Okay, and then the star there. Section D, fixed positions. How many different arrangements can be made using all the letters of the word if music if the letter M must be first? Okay, well, obviously, if M must be first, then let's just pretend we have our 5 boxes method, okay, for the 5 letters. If M is first, then I guess we only have 4 factorial different arrangements for the rest of the letters, okay? So that's sort of using a bit of logic and also um, using some common sense. If we have to have M being first, then that's already one combination that has to be fulfilled. So we can't have any more possible outcomes for that. It's just one possible outcome, and then we do our 4 factorial. So basically, it's like kind of excluding the fact that we can move our M around. So will only be arranging USIC. Okay, so that's basically what you do there. So that's going to equal 24 different arrangements. Same thing here. All right, we have chair, so 5 different letters, but R must be last. So we're technically only arranging chai. Okay, which is 4 letters, so 4 boxes, 4 factorial, and that's also 24. Okay, 6 people are sitting in a row. In how many different ways can they sit if one particular person must sit at one end? Okay, this is a bit different because say that let's draw a row. Okay, so we have 6 boxes. Let's represent them as people. Okay, there's actually 2 ends, right? So this is one end, this is another end. So there's 2 ends possible for our one particular person in the question. Okay, so but however, because we're only doing a fixed position for one of these ends, so let's say that our one particular person is person A. Okay, then we're going to be having the 5 other people rearranged accordingly as 5 factorial different possibilities. However, because A can also be at the end, okay, so this is, say, like if person was at the left end, okay, and then this combination here is if person was at the right end, sorry. Okay, so you can see here that we have actually double 5 factorial ways for these rearrangements to happen. Okay, so obviously with the other 5 people, that's 5 factorial. We know that from our previous question 9, question 10. We understand that, but because there's a left end and a right end in a row, you imagine 6 people sitting in a row, then you have to actually multiply 5 factorial by 2 because there's 2 different ends that the one particular person could be at. Okay, so we have to account for those 2 different positions for A, or person A, or that one particular person, which we'll call person A. So that's going to give us a value of 240 different arrangements. Let's try section E, mixed restrictions. So question 12 asks us to how many different arrangements can be made using all the letters of the word friend if F and R must be together and D must be last. Okay, so let's think of this as a step by step. I would start with the D must be last because I know that for fixed positions, they're pretty easy to work with because I can just basically cancel this letter out and everything else I'm rearranging, okay? Especially because this is a very one fixed position. I can't really do much with that. That's already one possible like arrangement. So I'm technically only rearranging my FRIEN, okay, which is 5 factorial, 5 different letters, which is 120 different combinations. Okay. However, moving on to section E, mixed restrictions. So question 12, how many different arrangements can be made using all the letters of the word friend if F and R must be together? So let's make that as a block. Okay, and D must be last. So if D must be last, then I can't change anything for that, right? So I'm only going to be rearranging these 4 different blocks, okay? So remember, if we have things that must be together, we count that as one block. And then 2 for I is, sorry, our third box is for I, third box is for E, and then fourth box is for N. So we have 4 factorial, okay? But we have to multiply by how many ways we can arrange FR. So that's FR and RF, which is 2 factorial. Okay, so that's going to give us 4 times 3 times 2 times 1 times 2, which is 48. Okay, different arrangements. Question 13, 7 students line up for a photo. In how many ways can this be done? If 2 particular students must not stand next to each other and 1 specific student must stand at the front. Okay, so very similar to question 12, just with different numbers. Let's say that our 7 students are A, B, C, and D, E, F, and G. That's 7 students. Okay, so let's say that A has to be at the front. Okay, so we can't do much with that. We're only rearranging the others now. But let's say that B and C have to be next to each other. So how many boxes do we have? We have 1 box, 2, 3, 4, and 5 different boxes. Okay, so that's 5 factorial times by the number of ways we can rearrange BC, which is 2 factorial because there's 2 letters. So that's going to be so question 13, 7 students line up for a photo. In how many ways can this be done if 2 particular students must not stand next to each other? So that indicates I need to be using my exclusion principle. So I'll be going back to section C and I'll copy this formula here. I've circled total permutations minus unwanted permutations, but I also have a fixed position. So I need to also consider that I can't change one of them there. All right. So yeah, let's have a look. Let's say that our 7 students are A, B, C, D, E, F, and G. That's 7 letters. So let's say that A has to be at the front, so I can't change anything there. If B and C, we'll assume is standing next to each other. So again, as I said, we're doing the total minus the unwanted. Okay, equals what we want, which is the must not stand next to each other. So if we know the unwanted, which is must stand next to each other, then we can do the total minus that to get what we want, which is must not stand next to each other. Okay, so I have how many boxes? 1, 2, 3, 4, 5. So 5 factorial times 2 factorial. Okay, that's going to be equal to my unwanted, where B and C must stand next to each other. And so that's equal to 240. Now the total, always take it as if there were no, I guess, restrictions. So well, I guess we can only take the total after we do the fixed position, sorry. So once we, consider the fixed position, because A can't change anymore. Like the student at the front can't change. So we're really only finding the total for 6 factorial, which is the if we were to not put B and C as the two particular students being next to each other. So it's going to be 6 factorial as our total. Okay. I might write that out just to be very clear. So we have A, B, C, D, E, F, G as our 7 students, correct? So let's assume that the one specific student, A, must stand at the front. So we can't do anything with A. The rest of the students, there are 6 number of students, okay? The total ways we can arrange them, if there were no restrictions in terms of the like standing next to each other or not standing next to each other, is 6 factorial, because we have 6 boxes, 6 different letters, 1, 2, 3, 4, 5, 6. Okay, and then we're minusing the 5 factorial times 2 factorial, where we consider if 2 particular students, let's say B, C, have to be next to each other. Okay, so we can find when they are not next to each other, which is the remaining possibilities, arrangements, number of arrangements. Okay, so that's going to give us 720 minus 240, which is equal to 480 different arrangements. Okay. Last section here to wrap this up. Common mistakes in reasoning. Question 14 asks us, a student claims when 2 objects must be together, you just multiply by 2. Is this claim correct? No. It's actually incomplete. Explain why this reasoning can be incomplete. It's because you only multiply by 2 after you treat the pair as one block, or if you're using the box method, like a box, and permutate the rest. Okay, so same thing what we've been doing here. We don't just multiply by 2 randomly, we have to multiply by 2 by the number of permutations where we consider those 2 objects being together as one box, and then the others are their own individual boxes. Okay. And question 15, in 1 or 2 sentences, explain the first step you should take when solving any permutation problem with restrictions. So the first step is always to identify the restriction first, and then choose the method, whether you have block or exclusion or fixed. Okay, and you can reference back to all the different sections in this video I've done, block, exclusion, and fixed in section B, C, and D respectively. And it's very important to don't jump to factorials only. Okay, so as a reminder in summary, always identify the restriction first, then choose the most appropriate counting strategy.